Okay, let's get started. Good afternoon, everyone. My name is Sergey Lebedev. I'm the product owner of Resistivity module in Starsteer. And today we are having a very special webinar where me from Rogi and Colleen from CHINOOK Consulting will be talking about vendor-neutral resistivity modeling and inversion, specifically on actual case studies, on actual data. Previously, we already had webinars on general introduction of vendor-neutral resistivity modeling and inversion, and today we are going to show you some case studies. Mostly, we will be talking about oil sands, Canadian oil sands, SAGD wells, where you steer a well very close to oil-water contact. But at the end, we will also show some wells where you can estimate anisotropy of your formation with the help of resistivity, and also how you can steer a well in a 3-layer formation, not only with gamma but with the help of resistivity, non-azimuthal resistivity. Yeah. Okay. So I was discussing the left when I was talking about the depth of investigation and compared to gamma ray, and on the second plot I was talking about differences between phase shift and attenuation resistivities. On the third plot, we can see that in horizontal wells we usually have several effects, and like in simple geology you should expect shoulder effect when you're approaching the boundary with different resistivity, and in that case your attenuation resistivity, for example, will start increasing first, indicating that you're approaching high resistive formation, and then following by phase shift resistivity. When you're crossing the boundary, if the resistivity contrast between those layers is high enough, you will get a polarization horn. You can also expect different separation between logs if you are drilling in formation that has anisotropy, or if you are drilling in formation that doesn't have a sharp resistivity contrast between layers, such as, for example, in oil sands, or near oil-water contact, where your resistivity can change gradually from high values to low values. And for that, you will need to model those responses. You cannot tell for sure only by looking at the logs what's happening actually. So, and also compared, for example, to gamma ray, all vendors that are present on the market, they have their own tools, they have their own specifications and designs, they have their own spacings between transmitter and receivers. They have slightly different frequencies, etc., etc. And that's why, and also usually all those vendors, they can do the resistivity modeling only for their own tools. And in Starsteer, we're bringing all those vendors and all those tools in our package. So anyone would be able to do the resistivity modeling and inversion of any resistivity tool. For example, here on the slide, you can have actual resistivity, and you can do the resistivity modeling. You can compare all those logs and understand, for example, relatively how far from the boundary you were. Or that was the forward modeling, where you have your model, you have your well, and you can do the forward resistivity modeling. Let's say you're already drilling your well, or you drilled your well, and you have resistivity logs. That's why, and you expect that you were drilling somewhere near the boundary with resistivity contrast. that's where our resistivity inversion will be helpful. So for the algorithm, you just select the logs that you want to put into the inversion, and then you will get a boundary as a result. So on top of just a standard stratigraphic approach, geosteering approach of gamma ray, where you do the correlation of gamma ray of your horizontal well versus offset well or type well, you will also do the resistivity inversion and resistivity modeling. Because you will not be able to do the resistivity correlation on a vertical track, because the resistivity profile depends very much on the angle between the angle of your deep of the structure and your trajectory, for example. So that was a brief introduction of our resistivity module. Going forward, I will give Kalin will talk about SAGD wells and how he used resistivity modeling in Starsteer for the wells in oil sands.
Yeah, so I will step a little bit back from the software and talk a little bit why it's important to use this methodology for thermal projects. And when we're looking at SAGD, it's clear that it's a very important part of the Canadian oil patch. When we started and expanded the geosteering services in unconventional reservoir, we always had the goal of applying this particular approach with a software-driven solution to oil sands development. And the reason is clear when you're looking at the production and reserves of Canada. Currently, 35% of the 4.5 million barrels produced today, of oil produced today in Canada, come from SAGD development. Even more, 78% of Canada's remaining 168 billion barrels of reserves are oil sands recoverable with the in situ method. So that's SAGD for the most part, CSS in part. So for this reason, it has been our focus at CHINOOK to provide improved services catering to this sector of the Canadian oil patch. And I know in the audience we have a lot of people that know a lot more than me about the McMurray Reservoir, but for the benefit of our international audience, I will talk a little bit about this play. So in this particular case, the McMurray Formation is complex on more than one level. There's different types of deposits: fluvial, deltaic, tidal, estuarine, and as such, they exhibit pronounced lateral variation. This poses a lot of challenges when it comes to geosteering. We have massive sands that are interbedded with shale beds and shale breccia in parts. We have these point bars that result in inclined heterolytic stratifications with dips at sharp angles relative to stratigraphy. A lot of the sedimentary features are developed just locally, and the reservoir character changes on a scale of hundreds of meters, sometimes tens of meters, even laterally. Some of these shale features that we encounter are barriers. Some are just baffles that can be percolated by steam and are not barriers in production. There's a lot of vertical permeability driven by ichneological features, boros, boring, and also the bitumen saturation is variable horizontally and vertically. We go and look at the thickness of the SAGD pay. It's variable within the McMurray Formation, and is generally confined at the bottom by bottom water or sometimes just the Devonian carbonates. Even if we're looking at this confine, the all-water contact, it's not always flat. Sometimes the underlying Devonian beds as well are affected by karsting. So the bottom line is it's a very complex reservoir. On the plus side, on the bright side, these SAGD boxes, the term we use for areas of SAGD development, they're thoroughly delineated, and we have strat wells every quarter mile, or about on average 16 wells per section. So very good well control. So when we go about developing these reservoirs, we have well pairs. A production well that is drilled very close to the bottom of the reservoir, and the steam injection well drilled at a set distance about above the producer. Then steam is injected in the upper well that heats up the reservoir, it mobilizes the oil flows down gravitationally into the producer well, and that's the CHINOOK SAGD. Now, we have to keep in mind, if a producer well is drilled too low into the bottom water, the energy is dissipated. If it's drilled too high, everything that's below it is bypassed bay. So it's critical to drill that producer well as close to the base of the reservoir, but above the oil-water contact. And that's what we're trying to do with, or trying to improve, I suppose, with geosteering these wells. And with all these complexities, it seems difficult to drill these wells, but it's actually not that hard, because at the end of the day, the only thing that we are chasing, and I'm talking about producer wells in this instance, we're chasing the resistivity contrast at the bottom of the reservoir, the resistivity contrast between red in water versus bitumen. So to geosteer McMurray Reservoir, and that means, as usual in geosteering, calculating the standoff to the base and the reservoir apparent depth, we need the ability to use resistivity logs for reservoir navigation. And I think it's a huge advantage to use it as part of a geosteering software, as opposed to just looking at the numbers given by us, to us by LWD tools. Historically, the big LWD service providers, starting especially with Halliburton, had a strong hold on resistivity data collection and interpretation throughout the 2000s. Things changed over the years. We saw oil companies starting to interpret the data themselves, mostly to cut costs, because Halliburton and other companies charged a fair amount of money for geosteering those wells. However, oil companies don't typically use this data as part of a geosteering software solution. And I think there are advantages to be had when using a said software solution such as Starsteer. This brings us back to last year at the Geo Convention. Roji announced the resistivity modeling and inversion module. It really caught our eye, and we have been talking with them for a while. And I think this, well, we realized that this aligns very well with our strategy for thermal oil sands jobs. So with that, we ran a project, a pilot project, where we used the LWD resistivity from Weatherford tools in that case, on an active SAGD development with Canadian Natural. And in the process, we developed a few workflows related to active reservoir navigation while drilling, and some connect workflows related to well placement planning. Since then, we ran these workflows on a couple other projects, and while we cannot show these data because they're a recent project, we picked another data set for this presentation. Let's see if you can go to the next slide here. This is our data set. We picked a project that we knew had great coverage with public data, with multiple LWD tools used or vendors used, and a few reservoir challenges specific to the McMurray play. This project was developed by Statoil at the time, Equinor today, since the mid-2000s, with 6 pads drilled just west of Conklin, and the original pads were followed up by a couple of infill campaigns. I believe it was 3 years ago where this acreage was sold to Arabasca, and Arabasca went in there and drilled another pad. So we accessed this data through the PetroNinja platform, and we collected data related to surveys, log data, also some production data. The LWD tools used, as we noticed, were Halliburton and Baker Hughes. We focused mostly on the Halliburton tools for this project. What we did was get all the data, and especially from the starting with the strat wells, we repicked all the tops, and we calculated the grids based on that. We obviously didn't have access to seismic data or any interpretation, so we used the raw data to basically reinvent the geosteering of this project. We used the Python scripts for this massive data set, which helped a lot with the speed of data acquisition. What I thought our workflow brought to the play was this using of multiple delineation wells to interpret a single producer. So as Sergey pointed out, the core of the resistivity modeling approach is simulating resistivity response of a particular tool based on an Earth model that in turn is based on adjacent type wells. This is actually very different than just projecting a wireline curve from an offset well along the horizontal panel or track. The math going into this simulated curves takes in account the interference between beds, physical specification of the tools, and a lot of other parameters. And where Starsteer goes a step ahead of maybe its competition is the ability to generate and use this Earth model based on multiple type wells. I don't think this comes right out of the box, but it makes it possible to use this approach. And this ability to use multiple offset, I think, is a strong point towards using this software for geosteering SAGD wells. The workflow that we developed leverages this ability by projecting multiple type wells onto the cross section and using combined models to simulate one single set of resistivity responses. And then, of course, comparing the simulated curves with the LWD readings in the graphical interface. And that would be our regular geosteering interpretation. So what we always want to do there is determine the stratigraphic position and apparent dips. And in this particular case, when we're talking about the SAGD reservoir, we want to determine the standoff to water, and in addition to that, the reservoir trends at the well scale. This is just one example of the wells that we did. Let's go to the next slide here. So we try to use geosteering software, and in particular Starsteer for geosteering SAGD wells before the resistivity module was released. Doesn't work very good. How would we normally conduct geosteering in a lithology like this? We would, of course, watch the resistivity values to approximate the standoff. For example, readings of 350 ohm meter would mean that we're about 1.5 meters from the oil-water contact. But that's not the type of precision we expect from a geosteering software. Now, this is a very variable, laterally variable reservoir. So we would rely heavily on grids and calculated surfaces to follow trends and for dip determination or approximation in this case. The correlation on the TVT scale, which is generally what we use for correlation in traditional geosteering, let's say, it's poor in this reservoir. The correlation is poor, and it becomes almost an afterthought when we use this when we geosteer this reservoir. TVT correlation is based on dip determination in traditional geosteering, so it feels very uncomfortable to dismiss that tool, but it just doesn't work in this geological setting, such as the McMurray. We need to look at a different approach and workflow for this, and that's where resistivity simulation or resistivity modeling comes into play. So that brings us to our workflow. We had actually a few slides prepared for this, but Sergey offered to demo the steps of the software on an actual inside the Starsteer. So I will relinquish the control there and Sergey can show us a little bit more how it actually works within Starsteer.
Okay, thank you, Colleen. Let's get directly to Starsteer. So in Starsteer, for those who are unfamiliar with Starsteer, it's a geosteering package, and we have several modules on working with geosteering data. So, for example, we have geosteering mode where you can do the correlation, strut-based correlation in a TVT scale on a vertical track, or you can do the synthetic log correlation in horizontal tracks. We have the assisted geosteering module where you actually software can help you steering the well or re-steer your previous horizontal wells. And now we added the resistivity module as well. So in resistivity module, if we click here, we have several submodes. So it's basically step 1, 2, 3. So before going to forward modeling, resistivity forward modeling, you need to prepare your model. So the algorithm would be able to do the calculation, do the resistivity calculations. And in order to do that, we do a log squaring of a type well. So let's see how it works. For example, in here I have my one offset well, and I see that this is my my SAGD resolver with relatively low gamma and relatively high resistivity. So we can see that resistivity can decrease on the intervals where we have slightly high gamma ray values, but on the interval with oil-water contact, we still have low gamma and low resistivity values. And at the same time, in several wells, we can observe that we have some kind of transition zone. So transition zone from low values to high resistivity values. And I can see that, for example, in this case, the resistivity in water is about 4.3 ohm meters, while resistivity above transition zone can be up to 200 or even 400 ohm meters. So let's do the log squaring. So when you create the logs, when you in that submode log squaring in Starsteer, you can select the type log that you want to square. So here it is, and I already clicked create squared log. So here it is. I can just drag it here and put it here. Let's make it more visible, like that. So right now I can play with the contrast and the thickness of the layers that I want to square. So in some cases where you have a very distinct boundary between a reservoir and, for example, shale, in that case you will usually make thicknesses of those blocks thicker, and you will adjust the contrast between those blocks as well. But in this case, I'm mostly targeted this transition zone because I know that my horizontal well is steered in this particular zone above oil-water contact as close as possible, but still not in oil-water contact. So I will make the thickness of my layers looking a little bit like that, and I will also change the MD range of the log, so to speed up the future calculations, because I don't need actually anything above here, and I don't need anything below here. So I will use this squared log as my initial input in Earth model for my model in my cross section. So right now we have Earth model under active interpretation, but I don't have any horizons. So let's create horizons. Again, I have tops picked in this type well from SAGD top, McMurray top, actually McMurray top, and then SAGD top. Where's my sand? And also the base would be the Devonian, and two tops with the transition zone and all water contact. So what I would do, I just click do the right click and click create horizons. Here it created the horizons for me. First the horizontal ones. So I see that my oil water contact grid looks like that, those dashed lines, and I know that this is my oil water contact. So I will first I will initiate the model looking something like that. So let's start from there. Okay, we have our squared log. Automatically, it appeared in here in the Earth model section in my resistivity ribbon. So I just click update Earth model, and the Starsteer will take those values from squared log and populate them along my horizons. So to be able to see that, I will select all my horizons in here. I will go to horizon format, and I will do the filling of Earth model with those resistivity layers. Let's try this palette. So the blue one would be my water, and there's the transition from low values to high values. Okay, right now we don't do any changes into Earth model, and I will try and to replicate and do actually forward modeling, and I will try to replicate my actual resistivity logs. On those resistivity logs, I can see that they're here relatively low values, then higher values, then the values decrease. And also I can see the separation between logs. I have 3 logs. They are just bulk resistivity. They are not azimuthal in here. While on the second track, I can see azimuthal resistivity logs. But in this particular case, in SAGD wells in oil, where you drill very close to oil water contact, you always know that your water contact is below. So that's why you have the azimuthal. For example, if you have azimuthal resistivity, usually it will tell you that at the top you can expect higher resistivity values. At the bottom you should expect lower resistivity values. And as a cost cutting, sorry, you can do the modeling, resistivity modeling in SAGD wells perfectly fine without azimuthal resistivities, only looking and modeling standard resistivity logs. So let's go to the forward modeling mode. Again, we are in resistivity mode in submodes, and in this submode I will click and select forward modeling. Again, my ribbon changed, and it's very simple. So what I need to do is just select a tool from the list of tools that I have. So I have lots of tools, and I know that it was drilled with Halliburton tool, and I can select and model any number of the logs that I want to model. But because we have those logs from those wells, so I will just select three logs and model their responses. So I just click run, and yeah, here they are. Let's also change the colors and change the values of those logs. So I will change it to blue, change it to black, and I will change this log to red. And let's make the line thicker. So the thick lines are my resistivity logs. So if I do some changes in the model, they will recalculate on the fly. So I will get a new resistivity response. Yeah, like that. But I can see that right now with my model, I don't get actual resistivity values as I expected from my log squaring. So let's undo and let's get to Earth model spreadsheet. So I can see that I have several layers and with different thicknesses and different resistivity values. I can and mostly I am concerned about these layers. So what I would do, I would just select all those layers and I will just delete them. These ones and probably this one. Okay. And I would do some manipulation with the resistivity values, with the resistivity profile. As I can see, my resistivity here changes from 4 to 300, and I still don't get the resistivity values close to that. So what I would, because I already did that, and it takes some time to find the best model for you. I will just change the resistivity values here to, again, gradually increasing from 4.3 because I observed that my the resistivity value in oil-water contact was about 4.3, and then resistivity values should increase. So I can do it simply like that, and I can just add another layer. And I will take that the area with the interval with pure oil with the resistivity close to 400. So that would be my resistivity profile. So you see that I changed everything going with the resistivity going from 4 to 400, gradually changing. And I can see that in my actual logs, the resistivity response was the resistivity profile was from, if we just talking about colors of those logs, from black to red to blue. And now I can see that I have same response, but with different values. So right now what you need to do is to actually do the geosteering, and because we know that our oil-water contact can change. So I would just change the position of those transition zone, and so we're starting getting a very good correlation between our actual logs and forward model logs. So right now here I can see and I can evaluate that actually I was at that distance from the all-water contact here. For example, here, if we make some slight changes again, I can get a different response. And you see that Starsteer will recalculate the forward model logs only on the segments where you do the changes. So if you have smaller segments, the calculation will be much faster. And for example, in this interval, I can see that I have high gamma values. So probably the resistivity, low resistivity values here was not only due to proximity of all water content, but also the content of high gamma. And for example, in here, I can see that my resistivity profile changed a little bit from black, red to blue, and my blue curve, which is actually the shallow phase shift reading the highest values. So I understand that probably here I was going farther from the all-water contact in this interval. So that was the showcase how you can do the resistivity modeling from, for example, one type well, and changing resistivity values in Earth model in order to obtain good correlation, good matching between your actual logs and forward model logs. It was just my brief interpretation. Here's the better one. So here's a very good interpretation. So I have the resistivity profiles from low to high resistivity. Here's perfect matching. Here I added some other layers in order to achieve the resistivity values due to high gamma content. Okay. So I think I'm done with with this well, and I will give control back to Colleen. And Colleen, if you would like to proceed with the slides.
Yeah, so I was mentioning that unlike Sergey, I will not go in there and change the numbers, but instead of that, we actually use the multiple type wells to generate those numbers in the Earth model. And that's what I'm going to present in the next few slides. But before going there, I would like to just have a few remarks about log squaring and the Earth model. Sergey explained that with the simpler log profile obtained with the log squaring, we get to much faster calculations when we do resistivity forward modeling or simulation. I think it has also another advantage by first of all identifying those contrasts, but also by using multiple wells that are, or multiple profiles that are squared, we harmonize the profile of the reservoir across the well bore. So we obtain models that make a little bit more sense mathematically. And then when we talk about Earth models, the way I see them is very much a 2D model along the well path or in the cross section. And I see them as a succession of stacked intervals of constant resistivity that are used then for our simulation. And then the modeled resistivity logs, there's three, from what I understand, I'm sure it's more complicated, but from what I understand, there's three variables or sets of variables that go into those calculations. One is the Earth model based on those squared logs. And by the way, they can be generated based on the logs directly. It's just not as efficient. So we have that Earth model that goes into the calculation. We have the technical specification of the tools coming from the vendors. And then we have the wellbore position in the model, the stratigraphic location, and the dip, because as we noticed, the resistivity response is different depending on the relative angle between wellbore and the stratigraphy. Once we create these Earth models and we go into the geosteering phase, the two things remain the same, that Earth model and obviously the tools. We are changing the stratigraphic location and the dip, our geosteering interpretation, and that's what we'll use to generate or to alter these synthetic curves, these simulated responses, to line them up with our actual LWD curves. So in other words, once we generate the simulated logs, we are recalculating that response based on our geosteering interpretation. What Sergey showed there was using just the one well profile and doing an interpretation based on that. Starsteer allows us to go a step further than actually than most current solutions on the market, and this is a very, very valuable approach, especially for a place like the McMurray, where lateral variability is such a huge factor. So what we do is we generate Earth models based on multiple type logs along the well path. We are looking here at this is our well path, and we have a bunch of strat wells along it. We create separate Earth models for each of these type wells. This is maybe close to the heel based on this well. We have another model based on this well in the middle, another one closer to the toe, and this one here, and then a fourth in this example based on this well that we can see here closer to the toe. We're all familiar with the Starsteer, and we know how you can have multiple interpretations or geosteering interpretation for each well, how you can run them at the same time, switch from one to the other. In the same fashion, we can generate separate interpretation, each with a separate Earth model. And we can use them separately, each in its own interpretation, or, and this is where our workflow is anchored in, combining all this into a single model to be used in a single interpretation, and we'll see that in a few slides here. So based on these separate models, we generate for each of them a set of simulated curves. Again, this type well here will generate these red curves. This other type well here, another set, and another set close to the toe. And these separate Earth models will then be combined into a combined Earth model, which is this one here at the bottom. Keep in mind, it's not yet geosteered, so it will not correlate with our LWD curves, at least not at this point. So we have one tool configuration, multiple models, multiple simulation, then we combine them. We combine the Earth models. So we generate a set of simulated resistivity curves that are different at various locations along the lateral. based on which how we combine the models. And we want to do this to be as close as possible to the type logs along the well path. By combining these Earth models, we have one tool set, multiple Earth models, and one simulation, one set of forward modeled curves. So this is how cross-section will look. And Sergey showed how we are painting our horizons based on the Earth model. And this is where it's different than just painting them based on the squared log in the first place. If it's just the one model, it would look the same. If you're using a combined model, now our model is different based on the different models that we generated. And we can look into the matrix here, into the spreadsheet of the Earth model. We have different sections with a range of thicknesses and a range of resistivities, and that's because we are using different squared logs from different type wells to generate this model. Yeah, I skipped this. This was an interpretation based on a single type log. And the correlation is not great, but good enough to give us an idea where the well is. And this is how service companies usually go about interpreting resistivity, right? You pick the most representative type log, and that resistivity response is then simulated along the well path. Halliburton and other LWD service providers simulate this response along in the planning stages, along a virtual wellbore dipping at 85 degrees typically, through an Earth model based on a single type well, on the most representative type well. Then they generate an artificial parameter, I believe it's called geosignal with Halliburton, and that quantifies the standoff to boundaries. That parameter is then used while drilling to approximate the standoff to water. With Starsteer's single model use, you can achieve the same results while matching simulated resistivity with the actual readings. And that will give us a pretty good idea about the standoff. Not very great, maybe, when it comes to the apparent dips along the wellbore. So if we go back to our combined model here, so now we have still a vertical stack of layer of constant resistivity, but it's different at different places along the vertical section. So this Earth model has become an array or a matrix of 2D cells that we use to generate this simulated resistivity curves dynamically. I need to point out as we adjust the geosteering interpretation, the apparent dip and standoff to water. The correlation is still done on this measure depth scale, but now we take into account the reservoir lateral variability. Typically, we combined 2 to 4 models, and the number of segments or these 2D cells that we talked about increases with every segment that we add. And let me go here. As we add more segments to our interpretation, so does this matrix of stacks of constant resistivity or of same resistivity. So we on the measured depth scale, we have different intervals, each with its own stack of thicknesses and resistivities. And again, this the resistivity simulation is recalculated dynamically, not instantly, but dynamically, and while we adjust our surfaces or our horizons. Correlation still takes place on this horizontal scale, as I said, and I think that is a shortcoming, but I don't think there's a way around it, because if we were to project to simulate vertical response based on our LWD curve, that's an equation with more than one solution. We would not be able to do that. Nobody is. So this is how we adjust the models. As usual with Starsteer, we have access to the raw data in the Earth model spreadsheet, but the data, as we can see, is a lot more complex and has more dimension. It has the TVD, thickness, resistivity values, measure that as it maps resistivity over the entire cross section. At this time, at least, thickness changes are not supported, so all these cells are rectangular. You have access to those values, as you've seen with what Sergey did there. He edit them directly because he can read the matrix. I wouldn't be able to do that, so I will just use what the software gives me from the squared logs. When you do your geosteering interpretation, you may notice a delay when adjusting boundaries, and that's as the simulated curves are calculated. I believe these are very complex calculations, and the simulation has to be recreated in all adjacent cells. That's why you will see these resistivity curves recalculated in all nearby segments. And that's horizontally and vertically has a weight in this calculation. It is not that much different than recalibrating a geomodel. It's just faster and more focused, as we are doing it all in a 2D model. So this is what we would have had with the correlation, poor correlation on the vertical space, use of variable thickness, honoring grids and surfaces, and then when we use resistivity, this is the results that we would have. And I only included this to show the difference between traditional geosteering with curve matching, if we can call it that, and the resistivity modeling. That very poor curve matching on the TVD panel is specific or very typical of this McMurray or similar reservoir. When we correlate the simulated resistivity with LWD curve, we have a much better chance to show a realistic interpretation of the well path within the reservoir. So that's the end purpose of this, to avoid the wet zones, give more more confidence and steering more aggressively closer to the bottom of the reservoir. There are pros and cons to each approach. I find that the correlation on the TVD scale leads to more precise dip determination. Resistivity matching on the horizontal scale is great for determining standoff to water, not that precise when it comes to trends in the reservoir. I would say that it gives you a upper end dip within 0.2 or 0.3 of a degree. And then we're not going to talk about azimuthal logs. Azimuthal gamma in inclined heterolytic beds has almost no value just because of the scale. We get readings every 0.2 of a meter or 1 foot, and these structures are centimeter scale. So it's not efficient at all. Then azimuthal resistivity. I know we're using it a lot in SAGD drilling. Question is, do we need it? I think it's very useful if we have a symmetric curve, if we would have a symmetric curve in a resistivity profile, not so much when we have a clear contrast and we know low resistivity is water, high resistivity is bitumen. And I believe at this time resistivity, azimuthal resistivity is not interpreted by Starsteer. I understand there's some changes coming with that. And this is just another example, another well. And just to summarize the workflow, 3 offset wells. One is actually off scale here behind the heel, one in the middle, one at the toe. 3 different models based on these wells, combine the models, obtain this synthetic curve. based on the combined model, and then use that to match and geosteer the well. Again, the correlation is done on the measure depth panel. Another example, this time water was intersected. Even with traditional geosteering, you would see that right away. The one thing that I would notice here is with the resistivity matching, you would see a trend. So you got a 90.2, 90, 90.7, 91.7. You would see that the reservoir is trending upwards, maybe prepare a little bit better when this event happened. And I don't think it could have been avoided, but anyways, it led to what 100 or 150 meters of a blank section here. I think we need to talk a little bit about limitations of this method. Everything is based on resistivity contrast. If you don't have resistivity contrast, your synthetic curves are flat. You won't be able to use this. Clearly, this approach is suitable for a very specific reservoir profile. Now, the McMurray and other thermal plays have bottom water or a basement with the contrasting resistivity. So obviously a great application for this approach. It is also applicable in other places with variable gamma and consistent resistivity, or the other way around in a place with flat gamma, such as carbonates, and specific reservoir resistivity signature. We are more and more drilling in depleted reservoirs. So what challenges that pose? Obviously, the resistivity profile will change when the fluid changes in the reservoir. Fortunately, here in the Athabasca oil sands, we have some control over that by drilling post-steam observation well logs, and we can use that as an additional reference. However, when we're drilling this type of wells, cuttings examination is paramount. And it has to be deployed along with geosteering in this cellar wells or wedge wells that drill in potentially depleted reservoir. Another potential problem, I talked a little bit about that, symmetric resistivity profiles. This is where azimuthal resistivity readings are extremely valuable. And that would be the solution to this problem. Azimuthal gamma, not yet supported. Sergey may have an update about that. Variable thickness, not yet supported. I would like to see some degree of variable thickness implementation, but so far we only focus anyways on the bottom of the reservoir and the transition to bottom water. So the method is solid when it from a reservoir navigation point of view, maybe not so much from a reservoir modeling point of view. Even with without the variable thickness. This is my last slide here. We grew this into a much bigger project, and I want to thank my team that helped me with encoding all the data, picking all the tops, and building this huge, massive data Starsteer project. What I want to point out here is that we can leverage Starsteer integration with Python here, and in this case as well. Many of the calculations and data export for large-scale project are very much accelerated with scripts that are relatively easy to write and even easier to execute. Infill planning, I did mention this a little bit at the beginning. That was another workflow that we developed with CNR at the time. It involves simulating the reservoir response for a directional plan, so not for an actual well while drilling, but for a directional plan in the planning phase. It also takes in consideration the geosteering interpretation for adjacent wells, and it goes a bit, well, a step beyond planning with the geomodel by simulating that response and getting this simulated resistivity values for these infill wells based on these close by geosteering interpretations. It might not be a big difference, but keep in mind that every meter above the base that that is left behind, that's oil left in the ground, and The threshold is really really thin here. We can only get so far before intersecting the water and losing reservoir energy. So good planning is critical. Everything helps there. And then data analytics are becoming more and more important, of course, and the new parameters and the workflows are developed all the time in order to better understand and develop the reservoirs. And it's when it comes to Starsteer, it's this combination of well placement with massive sets of data that includes log data, drilling data, production data, and the ability to access this with scripts, with automated scripts offer basically a great platform for data analytics. With that, I will pass the control again to Sergey, and he will let us know about the third applicability of this module.
Yes, thank you, Colleen. I would like to answer your concerns about not currently supported azimuthal LWD and also variable thicknesses changes. So we would be able to support some azimuthal resistivity tools by September, and working hard on implementing more azimuthal resistivity tools by the end of the year. And also I expect we would be able to work with variable thicknesses also by the end of this year. But as you mentioned, in most of the cases, you can have a couple of interpretations. One interpretation for resistivity, where you would use constant thickness, and you can overlay another interpretation with variable thicknesses, where you will not have a resistivity modeling, but you would have gamma ray matching, for example. I think let's check the questions before going to another applications. So let me check the Q&A section, and I have several questions.
Yeah, one of the questions there is about tools supported. I would just like to mention that we tried this approach with Halliburton tools, a little bit with Baker tools, quite a bit with Weatherford, and it's working great with those. We also got the chance of piloting one project with Schlumberger's periscope tools. Again, very good results, so I can test those. I'm not sure about the other ones.
Right, so we can just check the tools that we can support. So it's more than 10 vendors. The big 4 companies from Baker Hughes, we have this list of tools. Halliburton, we have this list of tools. Schlumberger, with the periscope, we have on the empirical one, which means that we support standard logs from the periscope, and Weatherford with those tools. Also, another company is also presented here. And right, as Colleen mentioned, we already tried modeling SAGD wells with Halliburton, Baker Hughes, and Weatherford, and in other formations we also tried using Schlumberger tools as well. Let's see other questions. So does it work with the thin layers and ramp resistivity profiles? Yes, it works. It might not be, so you need to use additional information such as gamma, for example. If you're steering in a thin layer formation, and if you have a very similar resistivity contrast on the top and bottom of that formation, you would probably get the same resistivity modeling if you are crossing the bottom or the top of formation. And that is why azimuthal logs would be helpful. But in many scenarios, you would steer and you would understand if you're approaching top or bottom of your formation with the help of other logs, for example, gamma, or with the help of regional trend of your structure. So, for example, if you're drilling with the 91 degrees and you're approaching some boundary, you expected that your structure would be subhorizontal, it's mostly probable that you're approaching the top of formation. So in that case, you would understand that you're approaching the top of formation, even with standard resistivities, when you will observe and you will model the separation between logs, where you will model the shoulder effect. Another question. How often do we end up steering just because of reservoir quality in the structure? I don't quite understand the question.
Yeah, I believe we do. Yes, but that would be again based mostly on information that we have beforehand on a geomodel.
Right.
Are we steering up where we expect increases or bottom water to be higher? Yeah, very much so. Again, that's not active geosteering, though. That is model-based geosteering. What this approach adds, though, is elimination of errors due to survey uncertainty. And we've seen it many times where the survey tend in one direction or the other, up or down, and we diverge from the geomodel. The trends are the same, but we observe a biased switch to or a trend towards one direction or the other. And then that's when we would use a direct observation and modeled or calculated apparent dips to actively steer the well away from those issues.
Right. Thank you, Colin. Another question, is resistivity data streaming to Starsteer supported? Yes, we can connect to any WITSML and stream data that is being transmitted through WITSML.
We can confirm that we tried it with Weatherford WITSML streams and it worked great.
Yeah. Okay. Thank you. Yeah, and I know that companies tried it with Schlumberger Interact as well. Another question. The problem with thin layers is that actually you don't see the real true resistivity due to anisotropy, and modeling is quite tricky. Yeah, that's right. So with the anisotropy, and I will show it in another well, what can we do? We can add the anisotropy value to any layer with resistivity values. So you would here on the third column you have your horizontal resistivity component, and if you know that you have anisotropy in your formation, or you cannot achieve that separation between logs or the value of those logs, you can try to add anisotropy in the layers, and you will observe that if the matching between actual logs and modeling logs is better, then probably you have anisotropy, and by trying different values, anisotropy values, you can get what kind of anisotropy you have. Thank you. Let's see what we have in chat section. So, Colin, there is a question for you, but it was sent privately from Valentin. I will read it to you. How do you keep the oil-water contact horizontal in the forward model so that it doesn't have the apparent formation dip? Would be impressed if you have this function to do a 2D forward modeling in Starsteer for horizontal oil-water contact and up dip information as shown in slides. Right. So I can answer that. So 2D forward modeling, we cannot support it yet, as we cannot do the thickness changes. I mean, we can do the thickness change in a standard geosteering model, but right now it's not supported in resistivity model. We would be able to do that in future. Okay, we have a great thank you from Michael. Thank you, Michael. And another question for horizontal drilling in thin reservoirs, do you make use of proactive geosteering? Yes, so like if you don't have azimuthal logs, you need to use some additional data, as I mentioned before, is either a structure, initial structure, so if you expect a deepen up or deepen down structure, or your resistivity contrast on the top and on the bottom is different. That's how you also can achieve a proactive geosteering, and I will show it in the third well. So I think we're done with the questions, and let me get to my second well. So, and in this second well, a couple of words on the inversion. So the inversion is the third step, third submodule in our resistivity module, and right now it's called two-layer inversion. And the reason is because we don't support azimuthal logs yet. That's why we ended up with only two-layer inversion for now. And it also works with any tools from the list. You will need only have actual resistivity logs. So in my first track, I have actual resistivity logs, and you see quite a big separation and polarizations in these intervals. On the lower track, I have my gamma, and as you understand here, with the higher gamma values, the well was escaping the reservoir, and that reservoir, if you look at the and the type log, so you can observe that this is quite thick formation, and the well was steered at the bottom of this formation. Namely, it's clear water. Again, it's Canadian well, clear water formation. And that's why we don't need actually azimuthal data. Again, we always know that our shale is below, so low resistive formation is below. That's why for our resistivity inversion, we can make some restrictions in the inversion parameters. So when I selected the tool that was used in this well, I selected the logs, for example, that I want to use for my inversion. I need to set up the MD range for those calculations, and I need to restrict the layers. So I would calculate high resistive formation at the top, and I would calculate low resistive formation at the bottom. So I should expect in here that my resistivity in top formation would be about 30 meters. So I would put this interval from 25 to 35, and at the bottom I should expect the resistivity about 2. So I would also restrict my bottom resistivity values about 2, right? And then I would say that my algorithm should search for the boundary plus minus 5 meters from the borehole. And this is the result. So if we click start, it will take some time, for probably about 3 to 5 minutes for this for this well. So I will just show you the result. And again, as you can see here, it calculated the boundary in here, where you don't have a very good separation between standard logs. Your boundary is far from the borehole. That means that it doesn't sense any boundary closer to the borehole. And again, here it senses the boundary, and going forward here it senses the boundary, and etc. etc. So if I will make an interpretation from this well, what I will do is to yeah, again, I can create horizons and populate the data from my squared logs, but we did it already and we are short on time. So I will just show you the result. So here is if we have our standard interpretation and overlay our interpretation over the inversion results. So you can also see that here my boundary was interpreted with the inversion pretty good here and here and in these areas as well. And with this my standard inversion, I ran the forward model logs. I did only 2 forward model logs and put them here. So I can put them in a separate track to see that they look very the same, right? So I was able to replicate these polarization horns and the separation between logs. So let's overlay them back on the first track, and I can show you that this my well is called anisotropy, right? So let me show why is that. So you see how resistivity values replicate actual ones. So here the blue curve is the shallow phase shift resistivity, and the red curve is deep phase resistivity. Separates like that, and the resistivity values about 5 to 7 ohmmeter. But clearly we went out of the formation in this part because we observe high gamma values. And if we look at the formation, we understand that we should expect in our shale and the resistivity not 5 to 7 but about 2, and in my sandstone I should expect the resistivity about 35 or 30 ohmmeters. So if I go to my Earth model spreadsheet again, I can see so this is the boundary. This is the boundary. So I have a layer of 30 ohmmeters at the bottom of my formation, and I have 2.3 ohmmeter at the shale below. But if I put anisotropy 1 for that formation of shale, I would end up with the resistivity values lower in this part than they actually are. Okay, you would say that I can just increase the resistivity value in shale rather than playing with anisotropy. And if I do that, for example, I will put 7, 2. Right, maybe 6. Yes, probably my resistivity in this part would replicate, right? The resistivity values would be very similar for the blue log and for the red log as well in shales, but you will not get the polarizations. And this is due to lower resistivity contrast that you put in your model. So 30 to 6, you will not get polarizations between those those layers. But if you put it back as 2.3 horizontal resistivity of your shale and increase the vertical resistivity value by changing the anisotropy value, then you will get logs recalculated, and you will get the polarizations modeled, and you would be able to understand how far from the boundary you were in this particular case. So that was the second example, and the third one, and that also was with the Caliburton tool, but another one. And this is the Schlumberger tool. So here you get the a 3-layer formation, but slightly different resistivity profile at the bottom and at the top of formation. And also it was a very thin formation, and it has a distinctive gamma increase at the bottom, and not that high increase at the top of the layer. So also we were able to replicate the resistivity profile with attenuation log and 2 phase shift logs. So if you make some changes into your interpretation, you will get the polarization moved a little bit, and you will understand that this is not the correct interpretation, and probably your structure was behaving like that in my final interpretation.
So thank you very much for organizing this, and thank you very much to everyone who attended. And hopefully we can deploy this on a larger scale on in more SAGD projects.
Yeah, thank you for joining me, and thank you everyone for your time. And hopefully you found this information very informative. And thank you.